Memories are super important topics in FPGAs, and today we will learn more about how to do memories in FPGA, both inside and outside, how to interface to that. This is EC 111 at UCSD, Lecture 10. First, we learn about the design flow for a data path. Whenever we have a data path, what happens is that we have a input-output coming to registers, and we have a clock which controls how data is coming in and out. And the primitive that we use to store data bits are flip-flops. Here we see an example of a flip-flop in System Verilog. This piece of code instantiates a flip-flop, and this is a library element that calls a flip-flop. So if we have a input and output as defined, we can have the clock and the data in here, and the data out is going to be in the queue elements. So in standard practice, what we do is we mix inference and instantiation. When we do inference, means that we have a code that could go on multiple targets. It's portable, which can simulate the generic simulator. And instantiation is when we do not have a portable code. We actually have a code which is specific to a design or a board, and it actually calls in simulation libraries to simulate. And this gives more control over a synthesis process. And very often, early on in the design, we may have portable code, or for portability reason, we may write portable code, but when you want to customize your design to a specific board, very often we go to instantiation of the board. And then when we use elements in a library, we need to use a simulation library that is specific to that target technology. We can't just go and generically simulate for every technology that we have. And we can have a more precise simulation once we have an instantiation in a certain technology than just inference of a particular element. So now, with that in mind, we go to how you instantiate register files and how memory is actually being used in various FPGAs and how we deal with it. So when we have register files, we typically can write to them and we can read from them, and for that we need a write address and write data going to this. Typically we don't have just one element, we have a stack of flip-flops, so we actually we don't have one bit, we have multiple bits. And then there is an address decoder here, so it actually decodes the address, and here is an address encoder, which you give it read address, and then again it's kind of giving out the read data. And now the question is, how do we implement an address decoder? Let's go to the board and see that. Here, this is how a decoder looks like. It gets the right address, and then based on the address it gets, it gives an enable signal to the register where we're writing the data, and then we write data to this element. So we decode the value of the address, we give it as a signal enable to the appropriate register, and then we write data to the registers. And this is how you would do this in System Verilog. We just have a register which has the output Q, and the input is the clock and enable, and the value in that we are writing into it. And when the clock comes, if this address is enabled, we are going to write to that register value. In this particular case, our register is 8 bits, so we are writing an 8-bit register stack using this command. things can get more complicated in real life. We may have more than one port or more than one address that you're reading and writing, and the actual memories are becoming multi-port. Here's an example of a dual port memory, how to implement the dual write port. So here, as you see, we have two decoders that decode each of the addresses. So as many ports as we have and how many addresses that we have the port addresses. Here, there are two decoders that are getting two addresses, and one of them is going to be selected to write the data to the particular register. So we can't simultaneously write to the same register, but we can have a selection of which port is writing to the register at the specific time that we have. And here's an instantiation for that example where we have a dual port. It's in this case, it's the enabled signal as we just saw here. So we have the enable coming to that register. We have the enable coming to that register. Oops. It's not working. Anyway, so, and then we have the address for the input and the data in and the data out, and what we are going to do is we are going to, if one of them is enabled, we are going to get the data in that is appropriate for that particular register. So pretty similar. In the next set, we will be learning about random access memory.